Very good afternoon, dear students. So we will continue with our network synthesis chapter. In the last class, we had talked about the procedure for network synthesis, where we had seen that how can we synthesize a network with the help of certain numerical examples. And since last lecture was very crucial and important with respect to network synthesis, I will also revise important concepts that we had seen in the previous class. Okay, so once we will hurriedly revise those concepts, and then we will move to further topic in the network synthesis. And today we will talk about the synthesis of special kind of networks, which are called LC networks. Okay. So first we will revise our previous class concepts, and then we will move forward. So let us review the important concepts of network synthesis from the previous class. So as I told you, network synthesis means the operational procedures through which a positive real function can be synthesized, and that positive real function is given in the form of either the impedance function or the admittance function. And impedance and admittance taken together is known as immitance. So somewhere in the books you may find the word immitance. So immitance is nothing but a combination of impedance and admittance. And as I told you, synthesis is said to be complete when all the network elements are known. So when it is told to you that you have to synthesize the network, it means you have to identify the values of each of the network elements which will be present in that particular network. And normally the long division procedure has been adopted to perform the steps of synthesis. Then I talked about this thing that we will have either the impedance function or the admittance function. And we discussed in the class that we will break up our impedance functions into further simple impedance functions, like ZS will be equal to Z1S and Z2S. Similarly, your admittance function is Y1S plus Y2S. And we know that the sum of impedance is equal to total impedance when impedance components are in series, and in case of admittance the summation is achieved when the elements are in parallel. So your first equation has been realized uh, through this figure, and your second equation is represented through this figure where y1 and y2 are in parallel. Okay. So then what we had seen for the impedance function, what we had done, we had identified whether our pole was present on your 0 or at infinity. So we had identified the simple poles. Okay. So for the impedance function, if we came across a term k naught by s, that means the pole is present at 0. Okay. That was segregated as this first term. And if our pole was at infinity, then this was the term k infinity s. And in case we have conjugate poles, pair of conjugate poles, this was the term that we had identified. So what we had done, we had splitted our impedance function into three things. One is your pole at 0, then pole at infinity, and then pole at imaginary axis. Okay, we had identified these terms, or we had extracted these terms, and then we had represented those terms in the form of network elements, either resistance or inductance or capacitance. So if you remember, this k naught by s term, it represents pole at 0. This k infinity s, it represents pole at infinity. And this term, where in the denominator we had s square plus omega square, that represented poles on j omega axis or imaginary axis. Okay. Then from this equation we had represented our, or synthesized our network like this term in the impedance function k naught by s represented a series capacitor. Okay. Then this k infinity s term, it represented series inductor term. or series inductor element. And this ZIS was your S square plus omega square term. This one, it represented uh, inductor and capacitor in parallel, but they are in total connected in series here. Okay, so L and C in parallel. And then after extracting these, we were left with Z2. So what our objective was, we first extracted this term out of the entire impedance function, then we extracted this, then we extracted this, and then we are left with Z2, and similar procedure will be followed with Z2 also. So we will keep on reducing our impedance function into smaller and smaller impedance function till we get the last element. So this approach we had followed in our previous class. I hope everybody has understood. So this was the series realization of the impedance function. And next what we have, this is your parallel realization of admittance function. So in case of admittance, we realize our network in parallel. So the terms that we had seen for impedance function, same terms have been shown in the admittance function also. But now since all these are admittances, so they will be in parallel. Okay, so in case of parallel realization, this K naught by S term, it represents inductor now in parallel. And I told you that your admittance function realization and impedance function realization, they are dual of each other. So the term which was in series in impedance function, that will become in parallel in admittance function. Then whatever we had a representation regarding inductor in impedance function, that will become capacitor in admittance. Similarly, the representation for capacitor in impedance will become representation for inductor in admittance. So you see, in case of impedance function, we had capacitor in the beginning and series capacitor, whereas in admittance function, that first term represents parallel inductor. So series become parallel, capacitor becomes inductor. Then this term in the series impedance function, this term represented series inductor. Here this term is representing parallel capacitor. Okay, and then this j omega axis or imaginary axis poles, in case of your impedance function, it represented LC in parallel, whereas in case of admittance function, it will represent LC in series. Okay, and then when we are left with Y2S, so similar methodology will be followed for Y2S also, and we keep on splitting till we get the last term. This is how we had represented admittance function, parallel realization. Okay, and students, why am I explaining these things again to you and reviewing all these things? Because in today's class, the synthesis of LC network is dependent on same thing only. I'm not going to tell many things new to you. These were, these will be just repetition of these concepts only, but with a different flavor. Okay, so this was our parallel realization of admittance function in ZS. Next. So if I summarize and if I in fact again tell you people what we identified the location of pole, whether our pole was located at S equal to infinity or S equal to 0. So for impedance function, if your pole is located at infinity, it represented a series inductor. Pole at infinity means we had a term HS or KS, something like this. Similarly, pole at 0, that means this term K by S. So in case of impedance function, this K by S represented series capacitor, and this HS or KS term represented series inductor. Similarly, for admittance function, the pole at S infinity. Okay, so S infinity again means HS. So this term for admittance, this term will represent a parallel capacitor. Okay, similarly, the term K by S, which represents pole at 0, it represents parallel inductance. Okay, fine. And regarding your imaginary axis, in case of impedance function, we had parallel LC elements, and in case of your admittance function, the imaginary axis poles, they represented series LC element. So it is again the same thing that I have explained in the previous slides. Okay, and just for your revision purpose, I have included one of the numericals that I discussed in the previous class. I'll hurriedly cover that so that you can understand the procedure to realize a given network or synthesize a given network function. So this was our impedance function, and this impedance function was expressed like this: to observe whether we have a pole at 0 or not. So since we have s in multiplication, so it means we have a pole at 0. And in fact, before we move that, the first step in the network realization, I told you that we will find out real part of Zs by putting s equal to j omega. So means we had calculated real part of z of j omega. So we will substitute s equal to j omega in this network function. Okay. And then we will find out its real part. And if that real part is having a constant value, that means some resistance term will be present in our network realization. And if it is 0, it means there is no resistance term. So this is what we had seen in the previous class. So what we did, as I told you, network synthesis follows the approach of long division process. So here we will have long division approach. So what we have done, this is our numerator, this is our denominator. And when we divide, we get 3 as quotient. So 3 is a constant that represents nothing but a resistance. Okay. So if we separate it out, we are left with this thing. So Zs is Z1 plus Z2s. And now we are left with this. Now we will extract elements out of this term. And I told you that in order to realize this, we will invert it and then realize it. Okay. So what we did, we inverted the previous term. So that was impedance term. And if we invert it becomes admittance. So we have this. So here, if you see, you have to again check whether there is any real part or not. So it has no real part. Okay. But you have one s term in the numerator. It means we have a pole at s equal to infinity. So if we have pole at s equal to infinity, it means there is a presence of parallel capacitor. So let us find out that. So we perform long division, we get 2s by 5. As I told you, the quotients of long division that will represent our inductor and capacitor and resistance value. So we get 2s plus 5. So we express our uh, previous expression as 2s plus 5, and this is the remaining one. We get y3 plus y4. And what is this y3? Y3 is nothing but a parallel capacitor. Okay, so it is cs. So what is the value of c is 5 by 2, sorry, 2 by 5. Okay, so your capacitor has been realized as parallel capacitor having value 2 by 5. Fine. Now what is our next step? We have realized this, we are left with this. We have to now simplify this. So we will again invert this. We have inverted. Okay, and if we solve this, what do we get? Your Z4 becomes 12.5s and this one. Okay, so since this is impedance function, the first term gives us series inductor and this gives us your series capacitor. Okay, and their values are, inductor value is 12.5 and capacitor is 1 by 10. So you see here, this was the resistance that we had identified. It was series resistance. Then we had identified parallel capacitor, and now we have identified series inductor and series capacitor. So this is our completely realized network function. Okay, so up to this point we had discussed in the previous class. For your revision purpose, to reinforce your concept, though I have covered only the most important part for your review, rest of the things you can again have a look at the recorded video that I have shared with you. Okay, So this is what I had covered in the previous class. I hope there is no doubt up to this point. So now we move to our today's topic, that is your synthesis of LC network. So you all know that your inductor and capacitive, they are also called reactive components. Okay, so we have resistive component and we have reactive components. So resistive components provide us the losses. Okay, our current is dissipated when we have resistance, and when we do resistance is zero, then our energy sources, they do not dissipate energy in the network. So that is the main point of LC networks, that is there is resistance is zero. Okay, so we will talk about reactive networks synthesis. In a way, you can say that this LC network synthesis is a special case of the network synthesis that we have discussed so far. Okay, because in those examples we had identified resistances also, or conductances also, but in LC network there will be no such case. So let us see what are reactive networks. Networks which do not contain any resistive element and which are lossless. You all know that when we have inductor and capacitor only present in the circuit, then no loss of energy takes place. We also get resonance, or there are oscillations. Oscillations are produced, continuous oscillations are produced when we have inductor and capacitor either in series or in parallel. Though practically it's not possible to have zero resistance, but if we assume that there is zero resistance, in that case, once that network is incited, the energy will never dissipate. Okay, it will keep on oscillating. So your oscillators will have resistances, inductance and capacitance. Okay, so these LC networks, they are usually called your reactive networks. Okay, and as I told you, for LC network also we will have driving point impedance and driving point admittance. So both combined together will be called as emittance. Okay, so your emittance can be obtained by combining impedance and admittance expression. So since we are talking about LC networks or reactive networks, we will have either the series combination or the parallel combination, as I told you in the previous slides also. So your series combination inductors will be combined in series like this, in capacitor in series like this. So we have equivalent representation of series representation like this. Similarly, your inductors in parallel will be represented like this. These are capacitors in parallel, and these are the equivalent representation. Okay, so before we talk about synthesis of LC networks, we must know the properties of impedance functions and admittance functions in LC network. As I told you, if you remember, we had seen the characteristics of network functions, characteristics of impedance functions, characteristics of admittance functions, that uh, whether the power of numerator and denominator, that should be there should be a difference of one only, all the terms should be present, or either only odd or only even should be present. Such kind of things we have discussed. We also talked about that coefficient of the polynomials in S, that should not be negative. So such kind of thing that we had discussed. As I told you that LC networks are the special case of these networks. So uh, there comes out certain properties which will help us in identifying the network just by looking at the network function. So if you look at the network function and you are able to identify the properties associated with those network function, you can say whether the given network function represents an LC network or not. Okay, so if a network function is given, you have to check whether that network function fulfills the characteristics of LC network or not. So in order to do that, you must be aware of the properties. So if these properties are satisfied, then we can say that given impedance function or the admittance function will satisfy those properties. So property number one. So first property is that in case of LC network, we will have the ratio of either even to odd or odd to even. This is very, very important point. What does it mean? That if you are being given ZS impedance function, and your impedance function is like this, for example, s raised to power 4 plus s square plus say 5, and in the denominator you have s cube plus 2s. What does it mean? That in the numerator we have all the even terms, that is ratio of even. In the denominator we have only odd terms. So this is a ratio of even to odd. So we can directly say that this is one of the properties of LC network. It could be reverse way also. Like you could have odd terms in the numerator and even terms in the denominator. Okay, so this is the first and foremost property of any LC network, that is it will be the ratio of either even to odd polynomials or odd to even polynomials. Then property number 2. Property number 2 is the highest powers of these polynomials in numerator and denominator, which are either even or odd, that must differ by 1. You can see here the highest power is raised to power 4, and here the highest power is raised to power 3. So there is a difference of 1. So this uh, must differ by 1, and the lowest power also differ by 1. You can see here we have s raised to power 0, and here we have s. Okay, this is your property number 2. Another most important property, that is your poles and zeros, they are simple, means they will not repeat, and they lie on j omega axis. What does it mean? That is your poles and zeros, they will lie on j omega axis. I told you that LC network gives us oscillations. Okay, oscillations. So for oscillatory circuits, your poles and zeros, they will be present on your imaginary axis. And remember one thing, we cannot have any pole zero in the right half. This is cancelled. We could have here any pole or zero present in this area. If we would have poles or zeros in this area, then there would have been certain constant term present in our poles and zeros that would have given us some resistive part. And since in LC network the resistive component is 0, that's why our poles and zeros, they must be located on imaginary axis. Okay, not in between. So that is another important point. Then property number 4, there must be a pole or zero at origin and infinity. What does it mean? As I told you, origin means 0, this one. Okay, this is your 0 of S plane. So this is also in a way present on j omega axis only. It satisfies that thing. And at infinity, infinity means it is, you can say, out of bound of this area of this. Okay, so you must have a pole or zero at origin and at infinity. Then next important property, residues. If you remember, we had represented our impedance function or admittance function in the form of partial fractions, different terms, as we had seen in the previous example also. And there we had certain residues, like say some a1 plus a2 plus a3. Okay, and obviously we had some terms like a1 by s. Okay, we had say a2 by s square plus omega square, a3 into s. So these are residues, a1, a2 and a3. These residues, they must be real and positive. That also we have seen in the previous class also. But for LC network, these residues must be real and positive. Okay, and then how will we obtain these various network components related to inductor and capacitance? We will perform a long division, and then they will give us the quotients, and those quotients will give us the values of inductor and capacitor. So these are the properties of any impedance function or admittance function which represents LC network. So if you are able to identify these properties, then you can see whether that network function is impedance or admittance function for LC network. So just for your homework, I have shown you two network functions, and you have to identify whether these driving point impedances functions, they represent LC network or not. Okay, so you do that because it is very very simple, so that's why I'm not explaining it in today's class. So I leave it to you as your homework to identify whether these network function represent LC network or not. You apply these properties these functions, and then find out. You will be able to get the answer immediately without much effort. Now let us discuss LC network synthesis. Okay, so dear students, your LC network synthesis, or you can say when you synthesize LC network, they can be represented in two forms. One form is known as Foster form, Foster's canonic form, and another form is Carver's canonic form. So you can say the two forms are Foster form and Carver forms. Okay, and further, these Foster forms, they are of two types: first Foster form and second Foster form. Similarly, we also have this Carver's form as two forms: Carver 1 and Carver 2. Okay, so in a way you can say that your LC networks, they can be represented with four forms of network. One is Foster 1 form, another is Foster 2 form, third is Carver's 1 form, and fourth is Carver's 2 form. Okay, so your Foster forms, they will have certain common things in the representation. Similarly, your Carver's form, they will have certain commonalities in the representation. Okay, so if you look at the two Foster forms here, you can see that your first Foster form, it is nothing but a series representation, and your second Foster form is parallel representation. And same concept applies to Carver also. Carver 1 represents series and Carver 2 represents the parallel representation. I hope all of you have understood this. And you can very easily see here that in series representation, we have already revised that we will have a series capacitor, then we have a series inductor, and then we have parallel LC circuits. And if we have parallel representation, there we will have a parallel inductor. So your series capacitor become parallel inductor, your series inductor becomes parallel capacitor, your series LC, parallel LC becomes series LC. Okay, and see, there is no resistance here. There is no possibility of any resistance present in these networks. So that means, like, if I talk about synthesis procedure and you find out real part of ZJ omega, that real part of ZJ omega will give you always 0 for the case of your LC networks. Okay, and rest of the things will apply, you know, the same that we have discussed or we have revised today. Okay, so that way my job is highly simplified. All that I have done is I have given a new name to series representation of LC network as first Foster form, and the parallel representation is given a new name, second Foster form. And for a particular case of LC network where your resistive component is 0. Okay, and I'll also take two examples to clarify both Foster 1 form and Foster 2 form for LC network. Let us see that. So first, let us talk about first Foster form of LC network, and we have already seen these expression. So these are the three terms that may be present. Your this is nothing but pole at 0, this is pole at infinity, and this is pole at your imaginary axis. And these are the three conditions only that we have talked about, that all poles and zeros, they will be present on imaginary axis. You must have some pole at origin and you must have some pole at infinity, or either one pole or 1 0, or both pole both 0. Any of these things may apply. So this term, it represents uh, this capacitor, this represents this inductor, and these terms, it represents your parallel LC combination. Okay, so this I have already explained to you. So this is your first Foster form. Then this is your second Foster form. So here again we have three terms. Okay, this is again pole at 0, pole at infinity. Then these are your imaginary axis poles. Okay, so it gives us parallel inductor, it gives us parallel capacitor, it gives us series LC. Okay, and in the text that I have shown in this slide, the same thing is mentioned here. This is your second Foster form. Okay, now let us have a look at one numerical example where we have to obtain Foster 1 form. So your in examination also you will get questions like this, that you have to represent a given network function in Foster 1 form. So whenever you are asked to obtain Foster 1 form, it implies that you must be given some impedance function. So if you are given admittance function and you are asked to realize Foster 1 form, then you should take the inverse of that. You should represent that admittance function into impedance function by writing 1 by y, and then realize that. Okay, so here we are given with ZS. So this is the network function. So we can see here that in the numerator we have all the even terms present, and then in the denominator we have all the odd terms present. Okay, and in the numerator the degree is s raised power 4, in the numerator the degree is s raised power 3, that is a difference of 1. Okay, then we identify that since the degree of numerator is higher, so we have one extra s in the numerator. Extra s in the numerator implies that we have a pole at infinity. Okay, then we have one s in the denominator also in multiplication. That means one pole at 0. So we have one pole at 0 and one pole at infinity. Okay, so it means we have both the elements, the first element uh, as well as the last element. So in case of your impedance function, what was the first element? If we have a pole at 0, the first element was your series capacitor. Okay, and the last element was your series inductor. So how to find out those values? We will express our given impedance function in partial fraction. So we can split this using partial fraction like this. Okay, and this is your capacitor term, this is your inductor term, and these are your imaginary axis poles. And we had proved in the last class that A2 and A2 star, they will be real and equal. So if you find out A2, this A2 star will also be A2. Okay, so let us do that. This was our given expression. This is our partial fraction approach. We have to find out the value of A naught. We have already talked about partial fraction approach in Laplace transform. So in order to find out A naught, we will multiply this entire with S. Okay, and substitute S equal to 0. So once we do that, we get A naught as 71.11. So A naught we have got. Then we have to find out A2. Okay, for A2 you will multiply this entire term with the S plus J3, and then you will substitute S equal to minus J3. Okay, and if you substitute, you get A2 as 19.45. This is our A2, this A2. Okay, and then we have to find out this, and if you look at this thing carefully and match, this h will give us the constant multiplier term. So this h is nothing but 10. Okay, so you can see here that by inspection we can see that our multiplier term is 10, which is nothing but h. Okay, so directly we can say that h is nothing but L infinity. that gives us 10 Henry. Okay, then this A naught we have obtained. So what is C naught? That is capacitor. Initially that is equal to 1 by A naught, and this gives us this one. So in your series network we have parallel LC. This is what we have. And this thing we have already seen, that in this parallel LC the value of C is nothing but 1 by 2 A2. So A2 we have obtained. So by substituting A2 we get C2 like this. Then L2 was 2A2 by omega n square. Okay, so you substitute A2, omega n square was nothing but 9. So this is 9, we get L2. Okay, so this is our L2. So we have obtained L infinity, C0, L2, C2. Substitute this thing in the general form of the network. So by substituting, we get this is the first form of Foster network. Okay, I hope this thing is clear to everybody. So, okay, students, after discussing this numerical example on Foster 1 form, now let us discuss one example on Foster 2 form. So we have already talked about that in Foster 2 form, we will have admittance function, that is ys, and I told you if you are given zs, you can take its inverse. So this is our admittance function. Okay, if we carefully observe this, we have admittance function numerator power s raised to power 4, in the denominator we have s raised to 3. So it means in the numerator we have even terms, in the denominator we have odd terms, and the numerator polynomial has degree 1 higher than your denominator polynomial degree. Okay, and if you carefully observe, the same condition lies as we had talked about in the previous numerical also. We have two poles, and one pole is lying at 0 and another pole is lying at infinity. So it means we will have the initial component as well as the final component also. So your initial component will be nothing but a parallel inductor, and your final component will be nothing but a parallel capacitor. Fine. So this is how our partial fraction will look like. This is your parallel inductor. These are your imaginary axis poles, which will give us series LC elements, and this is our parallel capacitor. Okay. So now you see, this is our given function. This is our partial fraction expansion. Okay, so we have to find out these residues B2, sorry, B0, B2 and H. These things we have to obtain. In order to obtain B0, we multiply this entire function with S and substitute S equal to 0. We get B0 equals to 1. In order to find out B2, what we will do, we will multiply the entire expression with S plus J2. Okay, and then we will substitute S equal to minus J2. If you do that and solve it, you get B2 equals to 1.125. Okay, and this H is nothing but by inspection you can see that what will be the constant multiplication factor in it. So you see the constant multiplication factor here is nothing but 1 by 4. So this H gives us 1 by 4. Okay, and this H gives us this parallel capacitor part. Okay, and the initial inductor, parallel inductor, is equal to 1 by B0, that was 1, and this is your this one. Fine. So we have obtained L0, we have obtained C infinity, which is nothing but this is your C infinity. Now we are left with L2 C2, which gives us series LC components. So what is L2? L2 is 1 by 2 B2. It is like the same formula that we talked about in previous numerical. Okay, so if you substitute B2, you get L2 equal to 1 by 2.25 Henry. Similarly, C2 is this one. So we have got L0, C infinity, L2 and C2, and you represent this as this form of network, and this form of network is called your Foster 2 form of the LC network. Okay. So dear students, with this I have completed one part of synthesis procedure of LC network, And what is that one part? That part one is the realization of Foster 1 form and Foster 2 form of the LC network emittance function. Okay, and we have seen that Foster 1 is your series impedance realization, and Foster 2 is your parallel admittance component realization. Okay, so I stop here.